kind of what these Taylor-Maclauring series are. They're just kind of fancy linear approximations. We're just adding a couple of more terms to make it more accurate. But let's just do a few more examples with some different functions, because it turns out that really what they have you do more often than Taylor series is Maclauring series. And the cool thing about Maclauring series is that a lot of terms drop out because of your derivatives. I mean, as we'll see here in a second, but if we do sine x, it turns out that because the Maclauring series is centered around 0, and the sine of 0 is 0, a lot of terms are going to go away. But you don't have to memorize that. You can just plug and chug each time. Some teachers will want you to memorize a list. Like they might want you to memorize the basic Maclauring series for sine x, cosine x, and maybe e to the x or something. But it turns out they're really straightforward. And as you see when we come up with this one for sine, it's really, even though this formula we're plugging and chugging into looks like a mess, we're going to get a lot of 0 terms. And because it's a Maclauring series, that means that c equals 0, because we're sort of centering our approximation at 0, meaning this goes bye-bye. You know, all these c terms go bye-bye. So we're just going to end up with powers of x, which is kind of nice too. So the answer is much simpler than the formula we're plugging into. All right, so the way we start on these things always is just to come up with our list of derivatives. And we didn't say how many degree, what degree to make it, but I'm going to say, I don't know, let's find the first 4 terms. Because why not? If you plugged and chugged through a few of these, you see that the 3 or 4 terms get to a very accurate approximation usually. So, first thing we want is a list of derivatives. If f equals sine x, then f double prime, single prime, equals cosine x. F double prime equals negative sine x. F triple prime equals negative cosine x. F quadruple prime equals negative sine x. That's positive sine x. And cosine x. So it turns out that with these terms, it looks like we're going to do, instead of a straight up alternating series, we go 2 positive, 2 negative, 2 positive, probably 2 negative after that. Keeps on going forever. All right, so our approximation is Maclauring series. First we need f of c, so we need sine of 0. Except, wait a minute, that's 0. Then we need so for our second term, we need f prime of 0, so we need cosine of 0, which is 1, times x. That was easy. All right, so f double prime of 0, so f double prime is negative sine, of 0 is 0. Oh, so that means this term goes away. Cool. So now we're ready for our next term. F triple prime, so f triple prime was negative cosine x. Cosine of 0 is 1, but negative times that is negative 1, so this is actually a negative term. And then we have a x cubed, and downstairs we have a 3 factorial. By the way, if you're wondering where these factorials come from, if you think about it, when you integrate something or take the derivative, don't you multiply by the same power again, like the new power? So if we started with x and we integrated it, we would get x squared over 2. And then if we integrated that, we would get x cubed over 3, but then we still have that original 2. And then if we integrate this, we end up with x to the 4th over 4, but then there's still that 3 and that 2 from last time. So that's how we get a factorial downstairs. And I'm not sure exactly how to explain it. Like, I don't know technically where it comes from, but the way I remember that a factorial kind of makes sense, and the way I sort of think of it as making a little bit of sense, that all these factorials are downstairs, is that if you integrate something a bunch of times, it is possible to get factorials sort of like spontaneously appearing. So that's how I remember it. All right, so if we go on to the next term, the 4th term here is once again going to be 0, because f quadruple prime was sine, which is 0, which means we move on to the 5th term, and we'll get the 5th prime. Oops, that's an accidental negative. So the cosine of 0 is 1, so that means our 5th term is going to have x to the 5th over 5 factorial. And you can see that what's going on here is that we're alternating plus minus, and we're only keeping the odd terms, because the even ones all end up with a 0 in them. So this right here is the Maclauring series 4 sine x. Pretty sweet. So you can see why it's not so bad to memorize that. If you do have one of those teachers who makes you memorize some basic Maclauring series, this is not bad in that it's just the odd numbers. And it turns out that cosine, so this is the sine expansion, the cosine expansion, because f would be cosine instead of sine, everything sort of shifts by 1. So the terms that are 0 this time would become 1 next time, and the ones that are 1 this time would be 0 next time. So it turns out the cosine expansion is going to look almost exactly the same, except it's going to have even powers of x instead of odd powers, and it's going to start with 1. So it's going to be 1 plus x squared, x minus actually, otherwise we'd go over 1, 2 factorial, plus x to the 4th over 4 factorial, etc. Hopefully I didn't just ruin a problem for us. All right, so find the Taylor series for this crazy function. So this is not one of your basic functions, but we know how to take its derivative, right? So we can just plug and chug through the formula. And in this one, let's just do however many terms we got here. All right, so f equals 4 times x to the minus 1/2. F prime is going to equal negative 4/2 times x to negative 3/2. And that was a negative 2, x negative 3/2. F double prime is going to be negative 3/2 times negative 2/2 is positive 3. X to the negative 5/2. And that's the last one I need. I don't need to go to f triple prime. You can kind of see how this pattern is going to keep repeating itself. We'll get different coefficients, but just x to the minus 5/2, x to the negative 7/2, etc. So we plug and chug through the formula. Now we're centering this one at 1, so that means that c equals 1. So what's f of c? What's f of 1? So for our first term is just f of 1. 4 divided by 1 is 4. Then we need f prime of c. So negative 2 times 1 to the whatever. The nice thing about centering this at 1, and this is not a coincidence that we picked 1, is because 1 to any power is just 1, so that's kind of nice. But teachers are usually nice like that. They don't tend to center things about wacky numbers that'll create a lot of roots and stuff in your answer. So negative 2 times 1 is just negative 2, so we get negative 2 and x minus c. Now f double prime of 1 is going to be f double prime is 3 times 1 is 3. So plus 3 over 2 factorial times x minus c, oops, we know what c is, squared. And if we wanted to, you could keep going, but we stopped here. But if you wanted to find f triple prime and then plug that in, and we can just get as many terms as you want. What's this one called? Well, this would be called P2, the second degree Taylor series, because we went up to this squared term right here. All right, good stuff. All right, there's another type of problem they'll sometimes ask you to do, and this is really straightforward. It's just kind of confusing directions possibly. So what they'll do is they'll give you the Maclauring series for something simple like sine x, and then they'll ask you to find the Maclauring series for that same function, but with a different argument. So they'll give you x, but then they'll ask for 3x, and they'll ask for x squared. So you might be thinking, it seems really easy and like too good to be true that I could just sub in 3x everywhere for x. You might be thinking, man, I bet there's a trick to it. I bet the chain rule is involved or some u sub craziness. It turns out it really is as easy as you hoped it would be. You just plug in 3x everywhere. So the sine of 3x is going to be 3x minus 3x cubed plus 3x to the 5th minus 3x to the 7th. Now you can see the fractions get pretty crazy because these denominators get really big. So we're just going to leave it in factorial form and everything. The thing I would caution you though is you want to be really careful that 3x goes in parentheses. So when we got 3x cubed, the 3 is also cubed. So there's actually going to be 27x cubed up top. So you just want to make sure if you ever did need to calculate this, and it would also be incorrect if you had written this term as 3x cubed like that over 3 factorial. and God forbid you did this, that would definitely be wrong, okay? So you've got to, this means 3 times x cubed, this means 3x quantity cubed. You've got to have parentheses there and apply the cube to both things. All right, we can do the same thing for sine x squared. So if you want to approximate sine x squared, it's going to be x squared minus x squared cubed plus x squared to the 5th, 5 factorial, and then minus x squared to the 7th over 7 factorial. All right, and we can simplify this a little bit. Just x squared cubed is minus x to the 6th plus x to the 10th over 7 factorial. Oops, over 5 factorial. Not sure where I got that. Minus x to the 14th over 7 factorial. All right, so that's what you can do if you know the Maclauring series or the Taylor series, whatever, and then they want you to find it, of just x. They want you to find the one of something like 3x or x squared or x cubed or 2x, whatever. Then you can just plug and chug, you can just substitute in really quick. And that's the reason to memorize these. So let's say you're on the test for this. You have a hard teacher. Your teacher gives, long, hard tests. So it'd be really great if you could sort of pre-memorize some stuff that would get you out of it. And one thing you can do, and especially if you're in like AP calculus and you want to get through the test faster, just memorize the sine x expansion, the cosine x expansion, maybe the e to the x expansion, and then you can just plug and chug through there. So if they ask you to find, the Maclauring series centered around anywhere else, you can just take the thing and then plug in. So if they wanted the Taylor series expansion, actually that would screw things up. All right, never mind. So this gets a lot more complicated. If there's a Taylor series of sine x, that's not the simple one with just x squareds in it. Now we're going to get in trouble. In the next video, we'll see some things that are not centered around 0 that get a little bit juicier. All right, last one of the basic Maclauring series. Because so far we haven't approximated functions much. We've just been finding the series. In the next video, we'll actually approximate functions, which is kind of a typical type of question they would ask you. All right, so find the second-degree Maclauring series for natural log of x. Sounds good. So c equals 0. So right away, the first thing I want to do is come up with my primes and whatnot. Oops. So f equals ln of x. F prime equals 1 over x. F double prime, since we're doing second degree, we want f double prime. So that's going to be negative 1 over x squared. Seems pretty good. All right, so f of, first thing we need is f of 0, which would be the natural log of 0. Uh-oh. Does anyone see a problem here? Then f prime of 0 would be 1 over 0, and yeah, none of this stuff exists. So it turns out you cannot do a Maclauring series for natural log centered around 0 because the natural log doesn't exist. And if you know what this graph looks like, the graph of natural log, it's the inverse of an exponential, so it goes like this. And it asymptotically approaches the y-axis. So if you try and plug in 0 to natural log, you'll get an error on your calculator. And similarly, the whole Maclauring series, the whole point of it is that you know the point. So like if you want to do Maclauring series centered around 0, the whole point is that you start with a point and then run your approximation from there, right? But if the point like at 0 doesn't exist, there's no way to do an approximation based on it. And that's why we're seeing this thing fail. So f of 0 doesn't exist. 1 over 0 doesn't exist. The second derivative at 0 does not exist. You got 1 over 0 squared. That doesn't exist either. So you can't do a Maclauring series around certain points. Now there is one subtlety, which is where every once in a while you'll see a teacher ask you to do something like, hey, find the Maclauring series expansion around 1. So you might be thinking, that's weird. How can you find the Maclauring series expansion around 1? The whole point of Maclauring series is that they're always centered around the origin, around 0. Well, here's the trick that they're asking you to pull. The trick they're asking you to pull to center it around 1 is to just add an offset of 1 to everything. So it turns out the Maclauring series centered around 1 is actually just the Taylor series and they're calling up the Maclauring series for no reason. But the point is you'll still end up with -1 here. So that's it. We'll work some examples in the next video.